solve the following non-homogeneous heat conduction problem. So we have a PDE, two boundary conditions, and an initial condition here. So if we compare this PDE with the standard PDE, this is the standard non-homogeneous heat conduction PDE, we get in our case R is just 1, P is 1, and Q, that is in fact, Q is in fact coefficient of U, which is, there is no U, so that's 0, and the non-homogeneous term, that's negative X. Okay, now if we separate the variables in the PDE, if we go up and look at this PDE, let's consider this non-homogeneous part 0 for now, and just consider ut equals uxx, and separate the variables here. Okay, and also in the boundary conditions here, by taking the usual u equals x times t, we get the boundary value problem. That means an ODE and two boundary conditions, x double prime plus lambda x0, where lambda is a constant, and x at 0 equals 0, and this. Okay, you can try on your own. Now we need to solve this eigenvalue problem, by the way. In that case, we consider three cases, as we've seen. So lambda 0, then just solve. After some time, you get a trivial solution. Second case, lambda negative, try in the same way, and we also get trivial solution. So we don't have any eigenfunctions. I mean, we have eigenfunction 0, no eigenvalues. Then third, lambda positive, just read through this, and we have a solution. So we get cosine mu 0, cosine is 0 where? Here, that's pi over 2, and here 3 pi over 2, 5 pi over 2, 7 pi over 2. That's odd integer over 2 pi. Okay, so the eigenpair, we get eigenvalues, these squares, and the solution, eigenfunctions are this sign. So you can read and find these eigenpairs. Okay, next we need to normalize these eigenfunctions, solutions of the problem. Not the original, just the eigenvalue problem. And to normalize, we just multiply this by something, by a constant, and multiplying by a constant still makes the function a solution. Okay, and we do in the following way. So the normalized eigenfunctions are just the eigenfunction times kn with this property. Kn times this whole thing is square dx equals 1, and kn is squared outside. This is sine squared is 1 minus cosine 2 theta over 2. So you find this. Now integrate and evaluate from 0 to 1. So you have this. So basically we get 1 from here. That means kn squared equals 2. So kn is root 2. So root 2 times the sine function, sine 2n minus 1 pi over 2x, for all n bigger than equal to 1 are normalized eigenfunctions. Okay, then by the formula, the solution of the given heat conduction problem is this series. Okay, this is the solution. uxt equals bn times phi and x, where phi and x are normalized eigenfunctions that we found earlier here. And next we need to work on these bn's. Okay, and these bn's are given here. Bn times e raised to, this is also provided formula, bn times e raised to negative lambda n t. Lambda n's are eigenvalues found earlier, plus 0 to t, this. Okay, this is the formula. Then we need to work on bn's and these new n's. Once we have, then we can combine. and integrate. Okay, so let's find first bn's. Again, bn's are given by this formula that we derived in class. Bn's are r times f times pn x dx. R is 1 and fx, that's the initial condition given in the question, by the way. If we go back and look at the original question, these are the initial condition, ux0. Those are given sine pi x over 2, and phi and x are normalized eigenfunctions here. Now we need to integrate this. We can pull this root 2 outside here. That leaves 0 to 1. Sine, let me specify this, sine 1 pi x over 2 times sine 2n minus 1 pi over 2x. And it's from 0 to 1. We know that these sine functions are orthonormal. Okay, and most of the time when we integrate from -1 to 1, it will be 0. Okay, unless when they are same. When 1 and 2n minus 1 are same, that happens when n equals 1. When we have n equals 1, this is 1, this is 1, then we get just L, which is 1 in this case. Okay, it's negative L to L, and when we have this we would get L, but we have only halfway, 0 to 1, and our L is 1, by the way, so we get L over 2. And that happens at one place, because in most of the places when we integrate this product we get 0. When n equals 1 we get L over 2, which is 1 over 2. So 1 over 2. Now I am writing this is true for n equals 1. Look at this. So we are supposed to find all bn's, but all other bn's are 0 for n bigger than or equal to 2. But for n equals 1, they will be same. Then we get L over 2, because it starts from 0, 1/2. Integral 0 to 1. Okay, 1/2. In fact, the whole value is 1/2. Here's a mistake. And the whole integral is 1/2. So anyways, root 2 times 1/2, root 2 over 2. That's b1. So we were trying to find bn's, so this part is done. Now let's find these new n's. Again, the formula is provided. New n's are found by the integral fxt. This is a non-homogeneous term in the original equation, phi n x dx. And this is given in the question, negative x. Go back to the original question, and these are normalized eigenfunctions, and we found these here. And we can pull -1 root 2 outside. Okay, this is -1 root 2 outside, and x times sine 2n minus 1 pi x. Now we can do integration by parts. So when we pull negative root 2 outside, that leaves 0 to 1 x times sine 2n minus 1 pi over 2x. And we do integration by parts. This is u dv, and evaluate and use this fact. Sine 2n minus 1 pi over 2, sine odd integer pi over 2, like sine 1 pi over 2, 3 pi over 2, 5 pi over 2, that is -1 raised to n plus 1. Using it shows up somewhere, and we get the whole thing here. -1 times this -1, 4 root 2, -1 raised to n plus 1 over this. Okay, and we can simplify, or pretty much this is a constant. So we have new n's. Okay, we could call this as constant as well. And this is true for all n bigger than or equal to 1. So if we look at the solution here, these bn's, because we are trying to find these bn's. Okay, I just found these new n's, and these bn's were also found. Only b1 would survive, all other bn's are 0. So let's work on this so we need to find bn in two ways now, because for b1, so b1 at that time we have some value, and when we find all other bn's n bigger than or equal to 2, then we only have this part because bn's are 0. So it's here. So I've rewritten here same thing, and I'm calling this is kn, just a constant. Okay, you can call anything. We might sometimes get a function of t, in this case just a pure constant. Now let's find b1t. We are supposed to find bn, but we have b1 non-zero, all other, this is root 2 over 2 I believe. Yeah, root 2 over 2, all other bn's are 0, so we need to find in two different ways. So b1 is just this, it's given, just writing n equals 1, and b1 is root 2 over 2, and lambda 1s are eigenvalues. Okay, go back earlier, first page, and look at that, lambda 1. Take n equals 1, we find negative is there, lambda 1 is pi square over 4t, plus here again lambda 1 is pi square over 4, and I have separated into two, e raised to negative lambda 1t, that part, times e raised to negative lambda 1 times negative s, just lambda 1 s, and lambda 1 is pi square over 4, first eigenvalue, s times this one we found earlier. Here if we take new, here n equals 1, take n equals 1, so 4 root 2 negative 1, so negative 4 root 2, and this is 1 square 1 pi square, so we have this. Okay, just coming from here k1, or we can say with n equals 1. Now we can integrate this, the front side is nothing, just keep writing the same thing over and over. Here this integral is with respect to s, so this t function we can pull outside, and this constant can be pulled outside, so these two we can pull outside of the integral, they are here. So 0 to t e raised to pi square over 4s ds, and we know how to integrate this. Okay, once we integrate we get this, or copy same thing over and over. Now we can distribute this inside, we don't have to, but I did anyways. I'm just multiplying this inside to this and to this, and 4 over pi square, 4 root 2 over pi square, this is here. Okay, and when I multiply this to this, first I get 1 because they have same power but opposite, so we get 1. So basically this negative negative positive, the whole chunk times 1 is this, and I'm just copying the left side. In fact you don't have to even multiply, you can leave here. And then what I did next is, here they are same, right? So we can factor that out, that leaves root 2 over 2 plus 16 root 2 over pi to the 4th. Okay, now finally we have the value that is in fact just 1, b1, and we need to find all bn's. So for n bigger than or equal to 2, all other bn's, the uppercase b is 0. If you go back, and 0 to t, this formula, same thing, and these are given by here. I mean, I have written kn, I should have written kn here just to simplify things. It's a constant in fact, and I can pull outside those kn's here, and I have e raised to negative lambda and t. Integrate this and evaluate it, upper limit lower limit, we get this. Now we can simplify multiplying inside. So these are bn's for n bigger than or equal to 2. Remember those lambda n's eigenvalues are 2n minus 1 squared pi squared over 4. So this is how we got all bn's. These for n bigger than or equal to 2, and we found b1's here, and our solution is in fact, it's already written here. Okay, we don't have to write them together. So the solution is just the sum of this. In fact, if you want to rewrite, this would have been for n equals 1, we have one part b1 times p1 x plus for n from 2 to infinity of all other bn's and pn's, and we found all the required things in this video. Okay, final